The most extreme objects scientists have found in space are defined by physical limits, by density, gravity, temperature, energy, and scale pushed as far as nature allows. Across the universe, matter and energy gather, compress, expand, and cool in ways that are consistent with known laws, yet far removed from everyday experience. This exploration begins by calmly observing those extremes, not as spectacles, but as stable outcomes of cosmic processes. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you'd like, you can share a thought or gently support the channel by subscribing. Now, let's begin. We start by clarifying what extreme means in a scientific sense. In astronomy and physics, an extreme object is not one that is frightening or dramatic, but one that occupies a boundary condition. It represents a point where a measurable quantity, mass, density, temperature, brightness, magnetic strength, or gravitational pull, reaches or approaches a known maximum or minimum. These objects are not rare because the universe seeks intensity, but because the processes that create them require long times, precise conditions, and large scales. Most of the universe is quiet. Space between stars is thin, cold, and dark. Even within galaxies, matter is spread out, moving slowly, interacting gently. Against this calm background, extreme objects stand out not because they disrupt the universe, but because they reveal what happens when familiar physical rules are applied under unfamiliar conditions. Gravity behaves the same everywhere, but when enough mass is compressed into a small region, its effects become unusually strong. Temperature follows the same laws of energy transfer, but when nuclear reactions or rapid expansion occur, the numbers rise or fall far beyond everyday ranges. As we move through this exploration, the pace remains steady. Each object will be approached as something stable, observed over time, measured carefully, and understood gradually. Scientists do not encounter extremes all at once. They detect small signals, changes in light, shifts in timing, subtle movements, and from those signals they infer the presence of something unusual but lawful. To understand extremes, it helps to first consider scale. Human experience is limited to narrow ranges. We live within moderate temperatures, moderate pressures, and moderate gravitational fields. Our bodies and senses evolved for this environment, so values far outside it feel abstract. In space, however, scale expands in every direction. Objects can be smaller than an atomic nucleus, or larger than entire solar systems. Time can pass in milliseconds or over billions of years. Extremes naturally appear when scale widens. Another important idea is balance. Extreme objects are often stable because opposing forces hold them in place. Gravity pulls inward, pressure pushes outward. Energy is released, but also lost. When balance is achieved at a high intensity, the result is an object that can persist for millions or billions of years. These are not fleeting anomalies, they are long-lived features of the universe. Consider density as one example. Density measures how much mass exists in a given volume. On Earth, dense materials like metals feel heavy and solid. In space, density can increase far beyond this familiar range. When a star exhausts its fuel, gravity may compress its core until atoms themselves are altered. The laws governing electrons and nuclei still apply, but under pressure so intense that matter takes on new forms. These states of matter do not violate physics, they reveal its deeper layers. Temperature offers another perspective. Temperature reflects the average motion of particles. In everyday life, this motion is modest. In stars, nuclear reactions drive particles to extraordinary speeds. Elsewhere, in the emptiest regions of space, particles move so slowly that temperatures approach absolute zero. Both ends of this range exist simultaneously in the same universe, separated by distance but governed by the same principles. light and energy also reach extremes. Some objects emit more energy than entire galaxies combined, concentrated into small regions. Others emit almost nothing, absorbing light instead. These differences arise from how matter falls, collides, or spreads out. Energy is never created without cause. It follows from motion, gravity, and transformation. As we proceed, it is useful to keep one steady thought in mind. Extreme objects are not exceptions to nature. They are confirmations of it. When conditions become intense, the rules do not change. They become more visible. Effects that are subtle in everyday settings become dominant. Time slows near strong gravity. Light bends. Matter rearranges itself into unfamiliar structures. None of this is chaotic. It is precise. Scientists learn about these objects indirectly. Very few can ever be visited or directly sampled. Instead, their presence is inferred through careful observation. Telescopes collect light across many wavelengths. Detectors measure particles and radiation. Instruments track timing with extraordinary precision. From these quiet measurements, detailed pictures emerge. This method of discovery shapes how extremes are understood. There is patience in the process. Signals are observed repeatedly, checked against models, compared across different instruments. Over time, confidence grows. An reminder of this is that many extreme objects were predicted by theory long before they were observed. Mathematics outlined what should exist if the laws of physics were consistent at all scales. Observations later confirm those predictions. In this sense, extreme objects act as tests. They show whether current understanding holds under pressure. When predictions match observations, confidence in the underlying laws deepens. When they do not, adjustments are made. This gradual refinement is part of how knowledge moves forward without urgency. Throughout this series, the focus will remain on observation rather than reaction. Each object will be allowed to occupy its place calmly. There is no need to rank them, compare them emotionally, or frame them as threats. They exist whether observed or not, following steady processes that unfold over immense timescales. You may notice that as descriptions continue, your mind adjusts. Numbers that once felt large begin to feel familiar. Concepts that initially seemed distant become more stable. This is a natural response to slow exposure. Understanding does not arrive all at once. It accumulates quietly. In the next section, attention will narrow slightly, moving from this general frame into specific examples. We will begin with objects defined primarily by density, places where matter is compressed far beyond everyday experience. The transition will be gradual, staying within the same scale of stellar remnants and gravitational balance. For now, there is nothing to hold on to, nothing to anticipate. The universe contains extremes, but it holds them steadily. Observation continues moment by moment without urgency. Neutron stars are among the most extreme objects defined by density that scientists have identified. They are the compact remnants left behind when a massive star has exhausted its nuclear fuel and collapsed under its own gravity. What remains is not an explosion, not motion, but a small, stable object where matter is packed to a degree found nowhere else in ordinary experience. A neutron star typically contains more mass than the Sun, yet it is compressed into a sphere only about 20 kilometers across. To understand this calmly, it helps to pause on the idea of compression. Gravity pulls inward continuously. During most of a star's life, outward pressure from nuclear reactions balances that pull. When the fuel runs out, the balance shifts. The outer layers may be shed, but the core collapses until a new form of pressure emerges. In this collapse, electrons and protons are forced together, forming neutrons. The star becomes, in effect, a giant atomic nucleus held together by gravity. The forces at play are familiar: gravity, nuclear interactions, quantum pressure. But they operate at intensities far beyond everyday conditions. This does not introduce new rules. It reveals how existing ones behave when pushed to their limits. The density of a neutron star is difficult to visualize, but it can be described precisely. A single teaspoon of neutron star material would weigh billions of tons if placed on Earth. This is not an exaggeration or metaphor, but a straightforward consequence of mass concentrated into a small volume. Yet even this description is only a pointer. The reality is best understood as a number, a ratio, a measured value, rather than an image. Despite this extreme density, neutron stars are stable. They do not continue collapsing indefinitely because another balancing force emerges. Neutrons, like all particles, obey quantum mechanical rules that prevent them from occupying the same state. This creates a pressure that resists further compression. Gravity and quantum pressure reach an equilibrium, and the star settles into a long-lasting form. Neutron stars are also defined by their internal simplicity. They lack the layered complexity of ordinary stars. There is no ongoing fusion producing energy. Instead, the star slowly cools over time, releasing heat accumulated during its formation. This cooling can take millions of years, and during that time the star remains nearly unchanged in size and mass. From the outside, neutron stars appear quiet. They are small, dim, and often difficult to detect. Their presence is usually inferred through subtle signals, radio pulses, X-ray emissions, or gravitational effects on nearby objects. These signals are consistent and measurable, allowing scientists to study neutron stars across great distances. One grounded observation comes from binary systems, where a neutron star orbits another star. By tracking the motion of the companion, astronomers can calculate the neutron star's mass with remarkable precision. These measurements confirm theoretical predictions, reinforcing confidence in the physical models that describe such dense matter. Over time, neutron stars may slowly change. Their temperatures drop. Their rotation may slow slightly. Their magnetic fields may weaken. Yet these changes occur gradually, without instability. The star remains, holding its extreme density in quiet balance. As this idea settles, it becomes clear that neutron stars are not defined by violence, but by compression and stability. They mark a boundary where matter cannot be packed further without transforming into something else. They occupy a narrow but persistent category within the universe. The next step will move from density to gravity itself, examining objects where gravitational effects become the dominant feature. The transition remains within the realm of stellar remnants, continuing slowly, without shifting scale or pace. Black holes represent a different kind of extreme, one defined not primarily by density alone, but by gravity reaching its observable limit. They form when a massive stellar core collapses beyond the point where even neutron pressure can resist gravity. What remains is not an object in the usual sense, but a region of space where gravitational effects dominate everything nearby. A black hole is characterized by its mass and its event horizon. The event horizon marks a boundary rather than a surface. It is the distance from the center at which gravity becomes strong enough that nothing, not even light, can escape. This boundary is not solid or visible on its own. It is defined mathematically, calculated from the mass of the object and the laws of gravity. From the outside, a black hole behaves much like any other object of the same mass. A star orbiting a black hole feels gravity in the same way it would around a dense star. This is an important stabilizing idea. Black holes do not pull objects in indiscriminately. Their influence follows the same inverse square law as all gravitational interactions. Only when something comes very close do the extreme effects become apparent. At the event horizon, time and space behave differently than they do far away. According to general relativity, time slows as gravity strengthens. To a distant observer, an object approaching the event horizon appears to slow down, its light stretching to longer wavelengths. This effect is measurable and predictable. It does not require speculation. It follows directly from well-tested equations. inside the event horizon, our current physical theories become incomplete. This does not mean chaos exists there. It means observation is no longer possible with present methods. Signals cannot return to the outside universe, so the interior remains unmeasured. Scientists describe this boundary carefully, distinguishing between what is known, what is inferred, and what remains open. Black holes vary greatly in size. Some are formed from individual stars and have masses several times that of the Sun. Others, known as supermassive black holes, reside at the centres of galaxies and contain millions or billions of solar masses. Despite these differences, the same principles apply. Gravity scales smoothly with mass. One stable observation comes from the motion of stars near galactic centres. By measuring their orbits, astronomers can calculate the mass of the unseen object they circle. These measurements consistently point to compact objects too massive to be explained by anything other than black holes. The evidence accumulates quietly over decades of observation. Black holes also interact with their surroundings. When gas and dust fall toward them, the material heats up, emitting radiation before crossing the event horizon. This radiation allows scientists to detect black holes indirectly. Again, the process is steady and observable, not sudden or dramatic. Over long timescales, black holes may slowly lose mass through a process known as Hawking radiation, though this effect is extremely weak for large black holes. For all practical purposes, they persist unchanged for durations far exceeding the age of the universe so far. As this section settles, black holes can be understood as regions defined by gravitational balance and limits of observation. They are not disruptions to cosmic order, but expressions of it. Gravity continues to operate consistently, even when its effects become extreme. The next section will step back slightly, moving to another stable stellar remnant, one less dense than neutron stars, yet still extreme by everyday standards. The pace remains slow and continuous. White dwarfs are another endpoint of stellar evolution, defined by extreme density and temperature, though less intense than neutron stars. They form when a star similar in mass to the Sun exhausts its nuclear fuel and sheds its outer layers, leaving behind a compact core. This core no longer produces energy through fusion, yet it remains hot and stable for a very long time. A white dwarf contains roughly the mass of the Sun compressed into a volume comparable to that of Earth. Gravity pulls inward, but collapse is halted by a different form of pressure. In this case, electrons resist being forced into the same quantum state. This electron degeneracy pressure balances gravity and creates a stable configuration. The material inside a white dwarf is neither solid nor gaseous in the everyday sense. It exists as a dense plasma, with nuclei packed closely together and electrons moving freely among them. The structure is simple and uniform, lacking the layered complexity of a living star. There is no core producing new energy, only stored heat slowly escaping into space. White dwarfs are extremely hot when they first form, with surface temperatures reaching tens of thousands of degrees. Over time, they cool gradually, radiating energy into the surrounding space. This cooling process is slow and predictable, taking billions of years. In this way, white dwarfs act as natural clocks, allowing astronomers to estimate the ages of star populations. One stable observation comes from binary systems, where a white dwarf orbits another star. In some cases, the white dwarf may accrete material from its companion. As mass accumulates, gravity strengthens, and if a critical limit is reached, the white dwarf may undergo a sudden transformation. This limit, known as the Chandrasekhar mass, marks the boundary beyond which electron pressure can no longer support the star. Below this limit, however, white dwarfs remain calm and persistent, most simply cool, fading slowly over cosmic time. Their light becomes dimmer and redder as energy drains away. Eventually, after immense periods, they are expected to become cold, dark objects sometimes referred to as black dwarfs, though none exist yet because the universe is not old enough. White dwarfs are common. They are the final state for the majority of stars in the universe. This prevalence gives them a quiet importance. They show how extreme density can be widespread without being rare or unstable. The universe contains many such remnants, holding matter in compact, enduring forms. As this idea settles, white dwarfs can be seen as intermediate extremes. They sit between ordinary stars and more compact remnants. They demonstrate how quantum mechanics and gravity cooperate to produce long-lasting balance. The next section will return to neutron stars, focusing on a specialized form defined not by density alone, but by another measurable limit: magnetic strength. The transition remains within the same stellar scale, continuing gently. Magnetars are a rare type of neutron star distinguished by the strength of their magnetic fields. While all neutron stars possess strong magnetic fields, magnetars occupy the upper extreme of this range. Their magnetic fields are the most intense known in the universe, reaching strengths trillions of times greater than Earth's magnetic field. To understand this calmly, it helps to recall how magnetic fields arise. In stars, they are generated by the motion of charged particles. When a massive star collapses into a neutron star, its magnetic field becomes compressed along with the star itself. Conservation laws require that as the size decreases, the field strength increases. In magnetars, this process reaches an exceptional level. The magnetic field of a magnetar is so strong that it affects matter at the atomic scale. At the surface, the field can distort electron orbitals and influence the structure of atoms. These effects are not speculative. They are predicted by well-established physics and supported by observational evidence from the radiation magnetars emit. Magnetars are observed primarily through their X-ray and gamma-ray emissions. Occasionally they release bursts of energy when stresses in their crust are suddenly relieved. These events are brief and localized, yet powerful. Even so, magnetars spend most of their existence in quiet rotation, slowly losing energy over time. A grounded observation comes from the regular monitoring of known magnetars. Their emissions follow recognizable patterns. The timing and intensity of their signals allow scientists to measure rotation rates, magnetic field strengths, and changes in structure. These measurements confirm that magnetars are neutron stars with unusually strong magnetic properties, not a separate category of object. Despite their intensity, magnetars are not common. Only a small fraction of neutron stars are thought to evolve into this state. This rarity suggests that very specific initial conditions are required during stellar collapse. Mass, rotation speed, and internal dynamics all contribute to the final outcome. Over time, magnetars gradually weaken. Their magnetic fields decay, releasing energy and settling into less extreme states. This process unfolds over thousands to millions of years, depending on initial conditions. Eventually, a magnetar becomes observationally similar to an ordinary neutron star. As this section settles, magnetars can be understood as an extreme expression of a familiar phenomenon. Magnetism behaves according to the same rules everywhere. In magnetars, those rules operate at the highest known intensities. The next section will remain with neutron stars but shift focus from magnetic strength to motion, examining objects defined by their precision and speed of rotation. The transition stays within the same conceptual layer, allowing the previous ideas to fade gently. Pulsars are neutron stars distinguished by the regularity of their rotation and the precision of the signals they emit. They are not defined by density or magnetic strength alone, but by timing. Among the most reliable natural clocks known, pulsars demonstrate an extreme form of stability in motion. When a neutron star forms, it often retains much of the rotational momentum of the original star. As the collapsing core shrinks, its rotation speeds up, much like an ice skater pulling in their arms. In some cases, the resulting neutron star rotates several times per second, or even hundreds of times per second. This rapid rotation is sustained over long periods with very little variation. Pulsars emit beams of electromagnetic radiation from regions near their magnetic poles. As the star rotates, these beams sweep through space. If one of them crosses Earth, it is detected as a regular pulse. The interval between pulses is remarkably consistent. Some pulsars maintain timing accuracy comparable to atomic clocks. This regularity is an observable fact measured over decades. Slight variations can be detected and accounted for, allowing pulsars to be used as precise tools for studying motion, gravity, and the structure of space itself. The extremity here lies not in violence or energy, but in predictability. There are different classes of pulsars. Some rotate relatively slowly, completing a few rotations per second. Others, known as millisecond pulsars, rotate hundreds of times per second. These faster pulsars are often found in binary systems, where interactions with a companion star have transferred angular momentum and increased their rotation rate. One stable observation comes from pulsar timing arrays. By monitoring the signals from many pulsars simultaneously, scientists can detect subtle disturbances in space-time, such as those caused by passing gravitational waves. This application relies on the extraordinary regularity of pulsar signals. Over time, pulsars gradually lose rotational energy. Their periods lengthen slowly as energy is emitted into space. This slowing is steady and measurable, providing insight into the internal structure and magnetic properties of the star. The process is calm and continuous, without sudden change. As this idea settles, pulsars can be understood as extremes of order rather than extremes of force. They show how an object formed through collapse and compression can settle into an almost perfectly regular rhythm. The next section will widen slightly in scale, moving away from individual stellar remnants toward the centers of distant galaxies, where extreme energy output is produced by processes operating on much larger scales. Quasars are among the most luminous objects scientists have identified, defined by the extreme amount of energy they release from relatively compact regions. They are found at the centers of distant galaxies, where a supermassive black hole is actively drawing in surrounding matter. The extremity here lies not in the black hole itself, but in the process of accretion that surrounds it. As gas and dust fall toward a supermassive black hole, they do not move straight inward. Instead, they form a rotating disk. Friction and gravitational forces within this accretion disk heat the material to very high temperatures. As it heats, it emits enormous amounts of radiation across the electromagnetic spectrum, including visible light, ultraviolet radiation, and X-rays. A quasar can outshine an entire galaxy, containing hundreds of billions of stars. This is a measurable fact, derived from observed brightness and distance. The energy does not come from fusion, as in stars, but from gravitational potential energy being converted into heat and radiation. Matter falling inward releases energy efficiently, making accretion one of the most powerful known energy sources. Despite this intensity, quasars are stable on long timescales. They can remain active for millions of years as long as sufficient material is available to feed the central black hole. When the supply diminishes, the quasar gradually fades, leaving behind a quieter galactic core. One grounded observation comes from spectral analysis. By examining the light emitted by quasars, scientists can determine their composition, speed, and distance. These measurements show that quasars were more common in the early universe, when galaxies contained more free gas. Over time, as matter became locked into stars, quasar activity declined. Quasars also serve as markers of distance and time. Because they are visible across vast stretches of space, their light carries information from the early universe. Observing a quasar is also an observation of the conditions that existed billions of years ago, preserved in the travelling light. As this section settles, quasars can be understood as extreme yet temporary phases in galactic life. They are not constant features, but stages that arise under specific conditions. The processes involved follow well understood physical principles applied on very large scales. The next section will remain within the realm of energetic events, shifting from continuous emission to brief but intense transitions associated with the end of massive stars. Supernovae represent an extreme in the sudden release of energy, marking the end of certain stars' lives. They occur when the balance between gravity and internal pressure within a star collapses, leading to a rapid transformation. Although brief on cosmic timescales, supernovae are among the most energetic events observed. In massive stars, nuclear fusion builds heavier elements in the core over millions of years. When iron forms, fusion no longer produces usable energy. Without outward pressure, gravity overwhelms the core. The collapse happens quickly, and the outer layers of the star rebound and are expelled into space. This release of energy can briefly rival the brightness of an entire galaxy. Despite their intensity, supernovae follow predictable patterns. Different types are classified based on their spectra and light curves. These categories reflect underlying physical processes such as core collapse or thermonuclear runaway in white dwarfs. Each type has characteristic energy output and duration. A stable observation comes from supernova remnants. Long after the initial explosion fades, expanding shells of gas remain, moving steadily through space. These remnants can be observed for thousands of years, providing insight into the energy and composition of the original event. The extreme moment gives way to long-term structure. Supernovae also play a key role in distributing elements throughout the universe. Heavy elements formed in the star or during the explosion are spread into interstellar space. Over time, this material becomes part of new stars and planets. The process is gradual and cumulative, not abrupt from a cosmic perspective. As this idea settles, supernovae can be seen as transitions rather than disruptions. They convert stored energy into motion and radiation, then return matter to the broader galactic environment. The extremity lies in the amount of energy released, not in instability. The next section will move to events even more energetic than typical supernovae, maintaining focus on stellar death while expanding the range of observed extremes. Beyond ordinary supernovae, there exist even more energetic stellar events, including hypernovae and gamma-ray bursts. These phenomena represent the upper limits of energy release associated with the collapse of massive stars. They are rare, brief, and highly focused, yet they follow consistent physical principles. A hypernova occurs when a star significantly more massive than the Sun collapses in a way that releases energy exceeding that of a typical supernova. The exact mechanisms are still being refined, but observation suggests that rapid rotation and strong magnetic fields play important roles. The result is an explosion that ejects material at extremely high speeds. Gamma-ray bursts are closely related to certain hypernovae. They are detected as short flashes of gamma radiation, lasting from fractions of a second to several minutes. These bursts are not emitted in all directions. Instead, the energy is concentrated into narrow jets that extend outward from the collapsing star. Only when one of these jets is aligned with Earth is the burst observed. This directional nature explains why gamma-ray bursts appear so intense. The energy involved is vast, but it is confined to a small region of space. When spread across a wider area, the intensity would be much lower. This understanding stabilizes the concept, keeping it grounded in geometry rather than scale alone. A grounded observation comes from afterglows. Following the initial gamma-ray burst, longer-lasting emissions at lower energies can be observed as the ejected material interacts with surrounding space. These afterglows provide information about the environment and the energy of the event. Despite their power, hypernovae and gamma-ray bursts are fleeting. They mark brief moments in the life of a star, after which the system settles into a new state, often leaving behind a black hole or neutron star. The universe absorbs the event and continues. As this idea settles, these phenomena can be understood as extremes of focus rather than duration. They demonstrate how energy can be released rapidly when conditions align precisely. The next section will shift away from explosive events toward extremes defined by size, exploring stars that occupy enormous volumes rather than releasing vast energy all at once. Some of the most extreme objects in space are defined not by density or energy, but by size. Giant stars, particularly red supergiants and hypergiants, represent extremes of volume. They occupy vast regions of space, extending far beyond the scale of ordinary stars while maintaining relatively low average density. These stars form when massive stars exhaust the hydrogen in their cores and begin burning heavier elements in surrounding shells. As energy production shifts outward, the outer layers expand dramatically. The surface cools as it spreads, giving the star a red appearance. Despite their enormous size, these stars can have densities lower than Earth's atmosphere. Red supergiant can extend hundreds or even over 1,000 times the radius of the Sun. If placed at the centre of our solar system, its outer layers would reach beyond the orbit of Jupiter. This comparison is used not for drama, but for scale, helping anchor an otherwise abstract measurement. The internal structure of such stars remains orderly. Fusion continues in layers, with heavier elements forming closer to the core. Gravity and pressure maintain balance, though the star exists in a delicate state. Over time, these stars lose mass through stellar winds, shedding material into surrounding space. A grounded observation comes from direct imaging and spectral analysis. Modern telescopes can resolve the surfaces of nearby giant stars, revealing convection cells and slow changes in brightness. These observations confirm theoretical models and show that even at extreme sizes, physical processes remain consistent. Giant stars are temporary. Their expanded state lasts only a fraction of their overall lifespan. Eventually, instability increases, leading to collapse or explosion. Yet during this phase, the star remains calm and luminous, evolving slowly over thousands to millions of years. As this idea settles, giant stars can be understood as extremes of expansion rather than compression. They show how energy balance can push matter outward, creating enormous but tenuous structures. The next section will narrow the scale again, focusing on compact extremes that occupy very small volumes while containing significant mass, maintaining continuity within stellar physics. Some extremes in space are defined by how much mass is held within a very small volume, even when the object is not as compact as a neutron star or as gravitationally dominant as a black hole. These compact stellar cores and remnants occupy an intermediate category, where familiar forms of matter are still present, but arranged under unusually high pressure. One example is the dense core left behind in certain stellar systems that have not fully collapsed. In these objects, gravity has compressed matter far beyond ordinary stellar conditions, yet not enough to force electrons and protons into neutrons. The result is a highly compact structure supported by quantum pressure, similar in principle to white dwarfs but often existing in more complex environments. These compact objects are often found in binary systems. Their extreme nature is revealed not by brightness or size but by their gravitational influence. By observing the motion of a nearby star, scientists can infer the mass and compactness of the unseen object. Small orbits and rapid motion point to something both massive and tightly confined. Temperature also plays a role in defining these extremes. Some compact objects retain significant heat from their formation, emitting energy steadily over long periods. Others cool more rapidly, becoming faint and difficult to detect. In each case, the physics remains consistent, governed by energy loss and pressure balance. A grounded observation comes from accretion behavior. When compact objects draw in material from a companion, the infalling matter heats up and emits radiation. The characteristics of this emission, its intensity, spectrum, and variability, provide clues about the object's size and structure. These signals are measured repeatedly, allowing careful classification. As this idea settles, these compact extremes can be seen as transitional forms. They bridge the gap between ordinary stellar remnants and the most extreme gravitational objects. They do not require new physics to understand, only careful application of existing principles under unusual conditions. The next section will shift focus from mass and size to temperature, exploring environments in space that reach the highest and lowest thermal extremes known, while remaining within observable, measurable limits. Temperature is another way scientists describe extremes in space, and it refers simply to the average motion of particles. When particles move rapidly, temperature is high. When their motion slows almost to a stop, temperature approaches its lowest possible limit. Across the universe, both extremes exist side by side, separated by distance and conditions rather than by different laws. The hottest environments known are found where energy is concentrated into small regions. The cores of massive stars reach tens of millions of degrees, driven by nuclear fusion. In more extreme cases, such as the material swirling near black holes or within powerful shock waves, temperatures can climb even higher. These values are inferred from the radiation emitted, which carries clear signatures of particle energy. In contrast, the coldest regions of space are found far from stars in vast interstellar and intergalactic spaces. There, particles are so sparse and so slow-moving that temperatures drop to just a few degrees above absolute zero. This background temperature is set by the residual radiation from the early universe, known as the cosmic microwave background. Both extremes are stable. Hot regions persist as long as energy sources remain active. Cold regions remain cold because there is little matter to absorb or generate heat. The balance is quiet and enduring, shaped by distance, density, and energy flow rather than by sudden change. A grounded observation comes from molecular clouds, where cold temperatures allow atoms to bind into molecules. These clouds can exist for millions of years at just a few degrees above absolute zero. At the same time, nearby regions heated by newborn stars may glow intensely, creating sharp but stable thermal contrasts. As this idea settles, temperature extremes can be understood as natural outcomes of energy distribution. Heat moves, dissipates, and concentrates according to simple rules. The universe accommodates a wide range without instability. The next section will shift from temperature to absence, examining regions where matter itself is scarce, and where emptiness becomes a measurable extreme. Not all extremes in space are defined by concentration. Some are defined by absence. Cosmic voids are vast regions of the universe where matter is unusually sparse. They are not completely empty, but compared to galaxies and clusters, they contain very little material. In terms of scale, they are among the largest structures known. Cosmic voids form as matter in the universe gradually gathers under gravity. Over billions of years, galaxies and clusters draw material toward them, leaving behind expanding regions with fewer particles. These voids grow slowly and predictably, shaped by the same gravitational forces that form dense structures. Within a void, distances between galaxies can be tens of millions of light years. Gas densities are extremely low, and star formation is rare. The environment remains quiet and cold, changing only over long time scales. This makes voids stable features of the cosmic landscape. A grounded observation comes from large-scale galaxy surveys. By mapping the positions of millions of galaxies, scientists can see the filamentary structure of the universe, with dense regions connected by strands and separated by wide empty spaces. These maps confirm that voids occupy most of the universe's volume. Despite their emptiness, voids are important. They influence how galaxies move and how light travels across space. Subtle effects, such as slight changes in cosmic expansion within voids, can be measured and compared with theoretical models. As this idea settles, voids can be understood as extremes of low density rather than emptiness. They demonstrate that absence itself can be a measurable condition, governed by the same physical laws as dense regions. The next section will move from emptiness back to mass, focusing on the largest gravitationally bound structures formed from many galaxies moving together. Galaxy clusters are the largest structures in the universe held together by gravity. They consist of hundreds or even thousands of galaxies bound into a single system, along with vast amounts of hot gas and unseen mass. The extremity here is not density in a small space, but total mass spread across enormous distances while remaining gravitationally connected. A typical galaxy cluster spans several million light-years. Within this region, individual galaxies move slowly relative to one another, following curved paths determined by the cluster's combined gravity. The motion is steady and persistent. These systems are not collapsing rapidly or flying apart. They exist in a long-term balance shaped over billions of years. Much of a cluster's mass is not in stars or galaxies, but in hot gas that fills the space between them. This gas is heated to tens of millions of degrees by gravitational compression and emits X-rays that can be detected by telescopes. These emissions allow scientists to map the structure and mass of clusters with precision. Another significant component is dark matter. Although it does not emit light, its presence is inferred through its gravitational effects. Galaxies within clusters move faster than visible matter alone can explain. This additional mass creates deeper gravitational wells, holding the clusters together. The behavior is consistent and repeatable across many observed systems. A grounded observation comes from gravitational lensing. Light from distant galaxies bends as it passes through a cluster's gravitational field. By measuring this bending, scientists can reconstruct the distribution of mass within the cluster. These measurements align with models derived from other observations, reinforcing a stable understanding. Galaxy clusters evolve slowly. Smaller groups merge over time, building larger systems. Gas heats, cools, and circulates. Galaxies interact gently, sometimes merging, sometimes passing by without direct contact. The scale is large, but the motion is unhurried. As this idea settles, galaxy clusters can be understood as extremes of accumulation rather than compression. They show how gravity organizes matter on the larger scales without urgency or instability. The next section will focus on motion itself, examining extreme speeds and orbits that arise naturally within gravitational systems while remaining grounded in observation. Some extremes in space are defined by motion, by how fast objects move or how tightly they orbit under gravity. These extremes arise naturally wherever mass and distance combine in particular ways. Speed itself is not unusual in the universe. What becomes extreme is consistency. Motion maintained at high velocity or within very tight paths for long periods of time. Near massive objects, orbital speeds increase. An object must move faster to remain in balance and avoid falling inward. Around neutron stars and black holes, this leads to orbits where matter travels at significant fractions of the speed of light. These motions are not chaotic. They follow precise trajectories determined by gravity and angular momentum. One clear example is found in accretion disks. Gas and dust spiral inward, accelerating as they approach the central mass. The inner regions of these disks are places of extreme motion, where particles complete orbits in milliseconds. Despite the speed, the structure of the disk remains stable over long durations, shaped by viscosity and gravitational balance. Another example comes from stars orbiting close to supermassive black holes. In some galactic centers, stars follow highly elongated orbits, swinging past the central mass at extraordinary speeds, then moving far away again. These orbits have been tracked over decades, allowing direct measurement of extreme velocities without ambiguity. A grounded observation comes from Doppler shifts. As objects move toward or away from Earth, the wavelengths of their emitted light shift slightly. By measuring these shifts, scientists calculate speeds with high accuracy. These measurements consistently confirm predictions made by gravitational models. Even at these extremes, there is no sense of strain or instability. Motion continues smoothly unless conditions change. Energy is conserved. Paths are repeated. The extremity lies in magnitude, not in disorder. As this idea settles, extreme motion can be understood as a natural response to gravity acting over short distances or large masses. Speed increases where it must, and remains steady where balance is maintained. The next section will move from motion through space to motion through time, examining how time itself behaves near massive objects, staying within a calm, observational frame. Time behaves differently in regions where gravity is strong or motion is fast. This difference is not subjective or perceptual. It is a physical effect ascribed precisely by the theory of relativity and confirmed through repeated measurement. In space, time itself reaches observable extremes, flowing at different rates depending on conditions. According to general relativity, gravity affects the passage of time. The stronger the gravitational field, the more slowly time passes relative to regions with weaker gravity. This effect is small near Earth but becomes measurable near massive objects such as neutron stars and black holes. Clocks placed closer to such objects would tick more slowly than clocks farther away. This is not a theoretical abstraction. Time dilation has been measured using atomic clocks on satellites and on Earth's surface. The same equations applied to these everyday systems extend smoothly to much stronger gravitational fields. Near extreme objects, the difference becomes larger, but the behavior remains consistent. Motion also affects time. As an object moves faster, time passes more slowly for it compared to a stationary observer. Near the speed of light, this effect becomes pronounced. In regions of extreme orbital motion, such as near compact objects, both gravitational and velocity-related time dilation can occur simultaneously. A grounded observation comes from signals emitted by objects in strong gravitational fields. Pulsars orbiting dense companions show timing shifts exactly matching relativistic predictions. These systems serve as natural laboratories, allowing time itself to be measured under extreme conditions. Despite these differences, time never stops or reverses in any observable region. It flows steadily everywhere, though at varying rates. The extremity lies in comparison, not in discontinuity. Each region follows its own rhythm, defined by mass and motion. As this idea settles, time can be understood as another quantity shaped by physical conditions. Its behavior changes smoothly, without sudden transitions or instability. The next section will step back from individual phenomena and begin to notice patterns shared across many different extremes, remaining factual and observational. Across the many extreme objects observed in space, certain patterns repeat. These patterns are not imposed by interpretation, they emerge naturally from measurement and comparison. By stepping back slightly, it becomes possible to notice how different extremes are connected through shared physical principles. One recurring pattern is balance. Extreme objects often exist where opposing forces meet at high intensity. Gravity is countered by pressure, motion by inertia, energy release by energy loss. Whether in a white dwarf, a neutron star, or a giant star, stability arises from equilibrium, not from excess. The extremity lies in the strength of the forces involved, not in their imbalance. Another pattern is transition. Many extreme objects represent stages rather than endpoints. Stars expand into giants, collapse into remnants, or explode and disperse material. Quasars flare and fade. Magnetars evolve into quieter neutron stars. These changes occur over timescales that are long compared to human experience, allowing each phase to persist and be observed. Scale is also consistent. The same equations describe phenomena across enormous ranges of size and mass. Gravity operates identically on planets, stars, and galaxies. Quantum effects shape both atomic particles and dense stellar cores. Extremes do not require special rules. They reveal the full range of familiar ones. A grounded observation comes from how predictions align across systems. Models developed to explain one type of object often apply to others with minimal adjustment. This consistency allows scientists to move calmly between categories, confident that understanding carries over. As this idea settles, extremes can be seen not as isolated curiosities, but as points along continuous distributions. They belong to a larger structure of behaviour that spans the universe. The next section will widen the perspective further, placing extreme objects within the long timeline of cosmic evolution while maintaining a factual, non-reflective tone. Extreme objects do not appear randomly in time. They emerge within the long, gradual evolution of the universe, shaped by conditions that change slowly over billions of years. When viewed within this timeline, extremes become milestones rather than anomalies, marking phases where matter and energy briefly occupy unusual states. In the early universe, conditions were hotter and denser overall. As expansion continued, matter cooled and began to collect under gravity. The first stars formed from simple elements, and through their life cycles, heavier elements were created. Extreme objects such as massive stars, supernovae, and early quasars were more common during these earlier periods because the raw materials and conditions favoured their formation. Over time, as matter became distributed into stars, planets, and stable structures, certain extremes became less frequent. Quasars faded as galaxies used up available gas. The most massive stars became rarer as heavy elements altered star formation. Yet other extremes persisted, such as neutron stars and black holes, which remain long after their formation. A grounded observation comes from looking at distant objects. Because light takes time to travel, observing faraway galaxies is also observing the past. Measurements show that energetic extremes were more prevalent billions of years ago, confirming theoretical expectations about cosmic evolution. This temporal perspective stabilizes the idea of extremity. What seems rare now may have been common before. What appears permanent may eventually fade. Change occurs steadily, without urgency, guided by the same physical laws throughout. As this idea settles, extreme objects can be understood as natural products of cosmic history. They appear, persist, and diminish according to conditions, not intention. The next section will turn gently toward the role of observation itself, examining how human instruments detect extremes without placing humans at the center of the story. Extreme objects in space are known only through observation. They are not experienced directly, but inferred from light, motion, and subtle changes measured over long periods. The tools used to detect them extend human perception without altering the nature of what is observed. Telescopes collect radiation across many wavelengths, from radio waves to gamma rays. Each wavelength carries different information. Dense objects reveal themselves through gravitational effects, hot regions through high energy emissions, cold, diffuse regions through faint background signals. No single instrument is sufficient on its own. Understanding emerges from combining many quiet measurements. Precision plays a central role. Timing must be accurate. Distances carefully calibrated and signals separated from background noise. This process unfolds slowly, often over decades. Extreme objects are not confirmed by single observations, but by patterns that persist across time and across independent methods. A grounded observation comes from repeated verification. When multiple instruments detect the same signal in different ways, confidence grows. This redundancy is essential when dealing with extremes, where intuition is less reliable. Measurement replaces expectation. Human involvement remains technical rather than interpretive. Instruments do not seek meaning or drama, they record data. Analysis follows established methods, comparing observation with prediction. When differences appear, models are adjusted quietly. As this idea settles, the role of observation can be seen as an extension of natural processes. Information travels through space, instruments receive it, understanding accumulates gradually. The next and final section will return the perspective gently to continuity, allowing the accumulation of ideas to soften and prepare the listener for rest. The most extreme objects scientists have found in space remain where they are. continuing their slow processes without regard for observation. Gravity balances pressure, energy spreads, cools, or concentrates. Motion repeats along stable paths. Nothing in this sequence rushes toward an end. Each state leads quietly into another. Across the universe, extremes do not interrupt continuity. They are held within it. Dense objects cool, massive structures drift. Time passes at different rates, yet always forward. The same physical rules apply everywhere, gently shaping outcomes over long durations. As attention settles, there is no need to retain detail. The ideas do not need to be organized or remembered. They can remain as a background sense of order. Processes unfolding steadily without urgency or demand. Observation can soften into rest. The universe continues its motion whether watched or not, carrying extremes and calm states together, without distinction. Everything flows. Sleep in that motion.